So, welcome to this lecture on combinatorics. In the last lecture, we have discussed the points on a selection of identical objects and some examples of selection of distinct books from a library, selection of items with identical objects. Then also we have proved one theorem of selection from identical objects. After that, we will see some selection with different objects. Also, we have discussed the proof of selection of at least one from each group. Yes. So, in this lecture, we have discussed combinatorial examples by continuing the partition of a group. Yes, and some theorems. So let us see here. First example of selecting fruits for a fruit basket. Selecting a fruit for a basket. So the example is a fruit vendor has a 5 identical apples, 4 identical orange and 3 identical bananas. Additionally, the vendor has 2 unique types of exotic fruits. The vendor wants to create a fruit basket by selecting one or more fruits. So, in how many different ways can the vendor create the basket? Yes. So, read again once again this example. We pause here for 10 seconds. So here 5 identical apples are given, 4 identical oranges are given, 3 identical bananas are given, and additionally the vendor has 2 unique types of exotic fruits are there, and we have asked to find the number of ways can the vendor create the basket. So for the apples, there are 5 identical apples. So there are how many choices are there? 5 plus 1 choices. For the oranges, how many choices are there? There are 4 identical oranges. That's why it is 4 plus 1 means 5 choices are there. For bananas, there are 3 plus 1 means 4 choices are there. And for exotic fruits, there are 2 unique types of exotic fruits are there. So that's why there are 4 choices for this one. And hence, the total number of selection is given by 6, 5, 4 is equals to 480. So by subtracting the empty set, what happens? By subtracting the empty set, we get 479 selection of identical objects or these fruits. Okay. So see here, this one. This is the second example, selecting the books for reading challenges. So the statement of this example is a student is participating in a reading challenge and has 6 identical mystery novels, 4 identical science fiction novels and 5 identical historical books. So the students also has 3 distinct biographies. The student plans to read one or more books. So how many ways can the student choose the books? So again, this is also same example. It is a parallel to the previous one. Just for mystery novels, there are 6 mystery novels are there. So 6 plus 1 is equals to 7 choices are there. For science fiction novels, there are 4 identical science fiction novels are there. So 4 plus 1 is equals to 5 choices are there. For the historical books, there are 5 historical books are given. So 5 plus 1 is equals to 6 choices are there. And for biographics, there are how many biographies are there? So there are 3 distinct biographies. That's why 2 cube means it is 8 choices are there. So the total number of selection is given by 7 the 5 into 6 into 8, so 1680. So by subtracting the empty selection by -1, we get the required result. Now let us see here the third example, creating a sandwich with ingredients. So let us see this one. So this is also the parallel to previous 2 examples. So read this example. A chef is preparing a sandwich and has 3 identical slices of cheese, 4 identical slices of ham, and 2 identical slices of turkey. So additionally, there are 3 different sauces available. So the chef wants to create a sandwich using one or more of these ingredients. So in how many ways can chef prepare the sandwich? So if you read this example carefully, you know there are 3 slices of cheese are given. It means that there are 4 choices for this cheese. After that, there are 4 slices of ham is given. Then there are 5 choices for this one. Then turkey slices are given here 2. So it means that there are 2 plus 1 choices, means 3 choices for this turkey. And for the sauces, there are 3 different sauces are given. It means that 2 raised to cube means 8 choices for this different types of sauces. So the total number of selection is given by 4 into 5 into 3 into 8, so 480, and by subtracting the empty selection we get the required answer or result. Yes. Now let us see here one theorem, and it is on maximizing the number of ways to select R elements. So see here the statement of this theorem. Given a set of n elements, the number of ways to select R elements is maximized with R is approximately n by 2. Specifically, when n is even, the number of ways is maximized at R is equals to n by 2. When n is odd, the number of ways is maximized at R is equals to n plus 1 by 2. So this we have to show here. So how we can show these results when n is even? Here already given there are set of n elements and R elements that we have to maximize, where R is approximately n by 2, and it depends on whether n is even or odd. So the number of ways to select R elements from n elements, we know that by combination formula it is NCR, and it is n factorial upon R factorial in another bracket n minus R factorial. So to find the maximum, we have to compare NCR and NCR minus 1. This ratio, yes, means NCR divided by NCR minus 1 is equals to n minus R plus 1 by R. So if this right hand side is greater than 1, it means that NCR is greater than NCR minus 1, and it implies that n minus R plus 1 is strictly greater than R, or we can say that R is less than n plus 1 by 2, and thus the maximum value of this combination of NCR occurs when R is close to possible n plus 1 by 2. So are you understand how we can how we can prove this? When R is close, then it is possibly n plus 1 by 2. So the first case, it is already given in the statement of the proof. When n is even, what happens? So when n is even, it means that n is, we can write in terms of 2m. So just you can put n plus 1 by 2 and replace n by 2m. So it is 2m plus 1 by 2, which is equals to m plus 1 by 2. And the closest integer to m plus 1 by 2 is n by 2, and hence the combination NCR is maximized when R is n by 2. So are you understand this case? Yes. So let us see now the second case. When n is odd, it means that it is a 2m plus 1. So just you can replace it 2m plus 1. So it is 2m plus 2 by 2. So m plus 1 is there, and hence the NCR is maximized when R is equals to n plus 1 by 2. Yes. So this is the theorem we have proved for which one? When the set of n elements, the number of ways to select the R elements is maximized when R is approximately n by 2, and we have proved the two cases when n is even or odd. So we conclude this lecture with this theorem. Thank you.